5.3 deals with what we were dealing with you lately with groups. It's just similar thing. So you have a ring, you have a special kind of subset of this ring. This special kind of subset is called ideal. So what makes a subset ideal? It is, let me write it maybe differently, closed under addition. So whenever you take two elements from this subset and add them together, result is again on this subset. And next one, it absorbs under multiplication. Now, so what is this? It's not precise somehow.
I know what it is.
So it's the same property as 0 has. 0 multiplied by anything is 0, right? So what this means, if you take any r in R and you multiply it by this whole I, result belongs to I. Of course, what it means that if you pick any element from I, this product is an I. That's how I wrote it before, right? If R is an R, I is an I, then Ri is an I. Okay? So these two properties make a subset of a ring ideal. So this closed under addition and absorption under multiplication tells you that in fact under addition it's a subgroup as far as addition is concerned, because of course difference is also there, right? Because you can multiply by -1, so 0 of course is there. So that's an ideal. Why ideals are interesting? Because with the help of this pair, you can manufacture a new ring, which is called factor ring. And what it consists of? It consists of classes of elements. What is the class of element R? In terms of elements here, which constitute it's R plus I. So analogy. Unfortunately, in your linear algebra, you probably didn't discuss factor spaces. There is a notion of factor space. It's exactly like here. You have a space, you have a subspace, and then you're making vector space out of this subspace and all shifts of it. So like you have a three-dimensional space, you have a plane, and all parallel planes. Planes which are parallel to it, okay? And out of these planes which are parallel to this given plane, you can constitute a new vector space. If you add two planes, result again will be a plane. How you will do it? What is a plane? It is original plane shifted by some vector. Another plane, original plane, the same one, shifted by some vector. What is the sum? Original plane shifted by some of these two vectors. And so, it's quite clear. So, similar story here. So you are considering these classes, and of course multiplication and addition of classes is given by these natural formulas, which you have to double check that they work. Because, again, you want operation between classes, not between elements. This one, actually, just based on closure on the fact that this is a subgroup under addition. But for multiplication, if you just ask for closure under multiplication, it won't work. You need this absorption property. So absorption property is necessary in order to be able to define product of classes. Okay. So that's about it. What?
Okay, so factor ring, factor group, all of these are like subsets of a factor set, right? To be more general, there's such thing as a factor set, right?
Yes.
Could you please
here you have additional algebraic structure.
Right.
So what you want it not just on set theoretic level.
Right.
You want to preserve your structure.
Right. My problem is that I don't really understand what a factor set is.
Factor set is the following. For us, probably the easiest way to look at it this way. Suppose you have equivalence relation on a set. You remember what is equivalence relation?
Yeah, but it seems so strange.
What is strange about it? It has very natural properties. Element is related to itself. If element is related to this way, then opposite way is also.
It's so generic though. If you give me a specific actual operation, be so better, so much better.
Well, maybe a good iteration is the following. Suppose you have a function from one set to another. Okay? Then your equivalence relation, one of the equivalence relations, the one which I have in mind is the following. D1 is related to D2. There are elements from here. By definition, if f of D1 is equal to f of D2. How about that?
That's a nice easy one.
That's a nice easy one. It clearly possesses all the properties.
This is equality.
This is equality, but it doesn't mean that these two elements are equal. They may be different. You know, maybe this function dumps all elements to one element.
Oh, dang it. Why'd you do that?
What?
Never mind.
Okay.
I mean, couldn't we just talk about like f of x is 2x plus 1?
Oh, well, 2x plus 1 won't be too good, because then every class will consist of one element. If you want to talk about it, then consider function f of x is equal to x squared.
Okay.
So what will be then? 1 will be related to negative 1, right? And x will be related to negative x.
Oh, you're saying this works for your...
If you take this kind of definition,
Oh, yeah,
with this function will be this, x and negative x are related.
Okay.
So every class consists of two elements, with exception of 0. 0 consists of one element. So that will be your equivalence relation. Okay, so then what you can do, if you have on a set equivalence relation, you can consider factor set. Set which consists of classes of equivalence under this relation. That's it. Since you don't need, you don't have any algebraic structure, that's it.
You said a factor set. Can you repeat your last statement?
Factor set will be a new set with elements which are classes of equivalent elements in the original set.
Okay.
That's it.
I feel like we should write that down or something.
So you have S.
Someone doesn't like to write things.
You have equivalence relation, right?
Okay.
So S and equivalence relation. So what is this? A set which consists of the classes of equivalence. Okay. So this is a new set. Elements of this set are not elements of S. It's some subsets of this element, of this set. Okay. So that's your general notion.
Can we do a numerical example?
Yes. Take Z, all integers. Take integer number which you like. Is there a number which you like?
Yeah.
Tell me.
12.
12. Okay. Take number 12. Consider equivalence relation which make two numbers real, not equivalence, I don't know, maybe it's equivalence. Consider relation which make two numbers related if their difference is divisible by 12. How about that? It's not hard to show that it will be equivalence relation, and this equivalence relation splits all integers into 12 classes. First class will be all numbers which are divisible by 12, which I formulate differently, which under division by 12 give me remainder 0. Next class will be all numbers which give under division remainder 1. Next would be with remainder 2, remainder 3, blah, 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 all the way up to remainder 11. Since I start numeration with 0, I have 12 classes. That's it, because I don't have any other remainders. So that's it. Now, if I consider set, which consists of this, with elements which are these classes, I will have just finite set with 12 elements. I started with integers, which is infinite set. I consider this relation. I check that it splits classes.
Yeah.
Classes don't overlap, because it's important. If classes overlap, then it's kind of hairy, right?
So you're saying Z12
Z12
factor
is this,
set.
yeah. But with this approach, I don't have Z12. I have just set of 12 elements. I'm getting Z12 when I say, oh, but Z is not just an infinite set. It's a set with a structure. Set which has addition and multiplication, which I can carry through to this 12 element set in such and such a way. And then instead of just set with 12 elements, I'm getting Z12, which also has addition and multiplication.
And it's a commutative ring.
And this is a commutative ring, according to our definitions.
Man, why did they, I don't know. Just
What?
kind of, like we learned about Z, whatever, ZN
Yeah.
a long time ago.
But that's what it, yeah,
But
okay.
at the time, I don't think we were using this terminology to describe it.
I think that's what
They
we
kind of
did.
built
We
on
had equivalence relation there, you know.
But
We
did
were
they call it
using,
a factor?
we was using maybe modular notations, but it's all the same. Look,
Yeah.
there are different ways to express the same thing.
Right,
There are different ways typically to prove the same theory.
right.
So what is to be upset about?
So, now can you give a brief overview of the factor ring thing one more time and maybe I'll get it?
Okay, so input in this situation. Ring and a subset with special properties. If I don't have the special properties, it won't work. What is happening with this stupid machine? Why it doesn't work? You know? I'm certainly pushing the right button. And it's nearly the end of the semester, so there is no much
Well,
need to be upset about.
I'm recording the audio for this.
By the way,
so,
is sound better there than here?
I've only listened to that one time,
Ah.
and I think actually sound is better here.
Here, okay. Well, so it was washout, but you know, nobody knew that you will come with such a sophisticated equipment.
Neither did I.
Yeah, yeah. Oh, by the way, I watched one of my lectures and I enjoyed very much. It's a great lecture. Okay, anyway. So, input is a ring and the subset with special properties. Output is new ring, which we can manufacture because this subset has these special properties. Okay. That's it. That's nothing else to me. Of course, it's nice if you look at examples, so make it more familiar. Now, these subsets may have some additional properties. May have some additional properties. We discussed with you, I think, 2 additional properties to discuss, to talk about special kind of ideals. Anybody remember names? There were some names attached. Blah ideals and blah ideals. What was it?
Principle.
So, I am beaten because that's the third one. That's I forgot about. I had 2. So, principal ideal. Very good. What is principal ideal? It's ideal sort of generated by one element. How it works? Whenever you have an element A in the ring, if you consider all elements divisible by A, which we can write like this, yeah? A multiplied by an element of R is kind of divisible by A. Yes. They satisfy these properties, they constitute ideal. Ideals like this are special, they are called principal, and that's standard notation. Okay, very good. There were a couple of others.
You got a prime ideal?
Very good. Or is it you are recalling it or you are reading
No,
it? At least you know where to read it also. There were prime ideals and another notion.
Maximal?
Maximal ideals. Okay, so I don't think that we discussed anything else. And you won't believe, I don't remember this terminology, though I'm kind of an expert in ring theory. But there are semi-prime ideals, primary ideals, this and that. It's too much. For me, I don't remember something. If I need to use them. But, okay, so, but these are 2 basic notions, because both prime ideals and maximal ideals are really important kinds of ideals. Prime ideals. Prime ideals have this property. If product of 2 elements of your ring belong to this ideal, it is necessary that one of the elements is in the ideal. course, it's sufficient. It's general definition, right? For ideal. If you have an element from the ideal and you multiply it by anything, element from this ideal, result is in the ideal.
You see one more time? The definition.
But here, stronger property. If product of two elements of the ring is in this ideal, one of them was in this ideal. Or how you can formulate it differently, if two elements do not belong to this ideal, their product also doesn't belong. So, I'll write it. I is prime if A, B is an I, then either A is an I or B is an I. That makes it prime. Okay? Now, why the word prime? If you look at this best example of the ring, interesting ring, which we have integers, then ideals, all ideals there are principal, but from the point of view of primality, only ideals generated by prime numbers are prime. What do I mean? Say, take number 6, which is not prime, right? Ideal generated by it is 6 multiply z, right? All numbers which are divisible by 6. But of course it's not true that if product of two numbers is divisible by 6, then one of these numbers is divisible by 6. It's certainly not true.
Mm-hmm.
So when it is true, when 6 is a prime number. Well, 6 is never a prime number, right? But product of two numbers is divisible by n, implies that one of these numbers is divisible by n only if n is prime. So that's why this term prime is preserved. Okay? Because they appeared in attempts, you won't believe it, to solve Fermat conjecture. Do you remember I mentioned that x in power n plus y in power n is equal to z in power n has only very special solutions when n is larger than 2? Attempts to solve this problem lead to understanding that we need to generalize some properties of integers to other rings, to some subrings of complex numbers. And there where this theory of ideals originally appeared and whatnot. Then, importance of this theory overgrew this problem. Problem was not solved on this way. It didn't work out, it was not enough. But these ideas were very fruitful, and so now we have prime ideals. Now, who can remind me what is a maximal ideal? Which ideal is maximal ideal? Okay, from the term, it should have some property of maximality. Now, of course, there is the maximal ideal, which we don't call this way, all ring. All ring is ideal, of course, in itself, and clearly, right, possesses all property. It's not interesting. So, first of all, it must be proper. It shouldn't be all ring. At least, not all. Okay. Second, it should be maximal in class of these ideals. So what does it mean? I have a ring, I have an ideal such that this ideal is not all ring. And second, if I contains M, strictly contains M, is not equal to it, then I is too large, necessarily whole ring. So, any attempt to enlarge this ideal so that the larger object is also an ideal will automatically push us to have whole ring. Okay? This is notion of maximal ideal. They also play a very important role. Okay? Example of a maximal ideal to broaden your horizons.
What's number 2 say again?
If I, which is an ideal,
Yes.
contains M and not equal to it, then I is whole ring. What's so upsetting about it?
So I
Okay,
is your
so it's
ideal?
the,
I must be an ideal, yeah. It's
Okay.
not just any subset which contains it. It must be also an ideal. So it's maximal in class of ideals. That's why it's called maximal ideal, right? So let me give you an example of a maximal ideal. Consider all polynomials. How about all polynomials?
don't you want to do Z something?
Hmm?
Don't you want to do like Zn or Z6?
No, unfortunately. Well, this I also can give you, but anyway, let's start with polynomials.
Okay.
Consider all polynomials and on top of it, of complex variable. How about complex variable? It's okay? Real numbers, complex. Okay. Consider all polynomials which are zeros in point zero. Not every polynomial. It's just polynomials without free term, right? Agreed? All polynomials without. I submit that this is an ideal. Indeed, if you don't have free term, in two polynomials if you add, they don't have free term, right? If you have a polynomial without free term and any polynomial, if you multiply them, no free term. An ideal. I claim that this ideal is maximal. That if you try to enlarge it, you will get all polynomials. How so? If I'm trying to enlarge it, it means that I'm trying to enlarge it by polynomial which has free term, right? Well, it has free term, and it's an ideal. I can multiply it by any number. I can assume that this free term is 1, right? Agreed? Because if it was 1/2, I multiplied by 2. If it was 2, I multiplied by 1/2. Anyway. Oh, okay. Now, this 1 plus remaining part belongs to our enlarged ideal. But remaining part belongs to our ideal, right? Because its remaining part is polynomial without free term, right? So I have C of x, right? And in this I have all polynomials without free term, right? And now I picked a polynomial p, which is here but not in here. So it has a free term, which is the same as to say p of 0 is not 0, right? Correct? Jared,
Huh?
wake up. So these are all polynomials without free term, right?